Hey guys, welcome back to another video. In today's video, we're going to be talking about limits inside of Calculus 1. So let's begin. What are limits? Limits tell us what values a function approaches when x gets very close to a value c. So in other words, if f of x becomes infinitely close to a single number L as x approaches c from both sides, then the limit f of x as x approaches c exists and it is defined as L. So to see that visually, we can use this picture over here, which basically states that the limit of f of x as x approaches c is equal to L. So to see that in action, let's do this question over here. So for this example, it says, what value does f of x equal to x approach as x gets very close to 5? So we're trying to look at the number 5. So this is the x-axis, and we're trying to look for 5, which is over here. So we're trying to see what value does the function, let's say, let's call it y equals x, approach when it gets very close to 5. So as you can see from the left, it just follows here, and when it reaches 5, the function also reaches 5 over here. So from the left, the function approaches 5, and from the right, the function also approaches 5. So that you can say that the limit of x as x approaches 5 is equal to 5. Let's move on. So right here, we're going to be talking about some properties of limits. So for this first property, it says that the limit of a as x approaches c is just going to be a. This is because a is a constant and it doesn't change at all during its domain. So for whichever value you get close to, it's just going to equal to a. So for this question, it says find the limit of f of x equal to 5 as x approaches 6 from both sides. So the function is y equals 5. And we're trying to see what value does it approach when it gets really close to 6. So this is 6 over here, and we're trying to see what happens over here. So from the left, it just stays constant. It's always 5. So from the left, it approaches 5, and from the right, it also approaches 5, which means that the limit of 5 as x approaches 6 is just going to be 5. Okay, next slide. So for this next one, it says that the limit of x as x approaches c is going to be c. So to see that, let's say we have some function f of x is equal to x as x approaches 4 from both sides. So we're looking at c equals 4, so 4 is right here, and we're trying to see what value does the function approach as we get really close to 4. So from the left, the function just goes up normally, and it reaches the number 4. So from the left, the limit is 4, and from the right, the limit is also 4. So over here, the limit of x as x approaches 4 is going to be equal to 4. For this third property, it says that the limit of x to the power of n as x approaches c is equal to c to the power of n only if n is greater than 0 and that it is an integer. So we have this question here that says we need to find the limit of f of x that is equal to x squared as x approaches 2 from both sides. So we're trying to look for x equals 2, so x equals 2 is right here. We're trying to see what value the function approaches. So from the left, the function approaches 4, and from the right, the function also approaches 4. So now we can say that the limit of x squared as x approaches 2 is going to be equal to 4, or 2 squared as shown here, so which is also equal to 4. So these are some more properties. So whenever the limit of f of x exists and that it is equal to L, you can say that the limit of f of x as x approaches c is equal to L. And you can say the same thing when the limit of g of x exists, and when we say that it's equal to m, we can say that the limit of g of x as x approaches c is equal to m. So with this first property over here, if k is a real number, then the limit of k times f of x as x approaches c is the same thing as k times limit of f of x as x approaches c, or KL, because we said that the limit of f of x as x approaches c is equal to L, so it's basically L, K. So K is basically like a scalar, it like multiplies, so it's like some constant, let's say it's like 5L. So we can have like 5 limit, or 5 in here, it would be like the same thing. And for the second one over here, if n is an integer greater than 0, so n is greater than 0, it has to be an integer, then the limit of f of x as x approaches c to some power of n is the same thing as the limit of f of x to the power of n as x approaches c, which is the same thing as L to the power of n, because remember we stated that the limit of f of x as x approaches c is equal to L. So we can sub this in as L to the power of n, which is just the same thing as L to the power of n. Okay, let's move on. So these are some more properties. So it says that the limit of f of x plus or minus g of x as x approaches c is the same thing as the limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. And remember, we defined that the limit of f of x is equal to L, and that the limit of g of x as x approaches c is equal to m, as you can see here. So we can use something similar for this one, as it says that the limit of f of x multiplied by g of x as x approaches c is the same thing as the limit of f of x as x approaches c multiplied by the limit of g of x as x approaches c, which is the same thing as L times m. For this third one down here, it says the limit of the quotient f of x over g of x as x approaches c is the same thing as L divided by m, whenever m isn't 0, because whenever it's 0, it's undefined, because when you divide anything by 0, you reach a really big number. Over here it says that if c is a defined value on the domain of a given function, so let's say there's like some function here, and this is c, and up here is f of c, and this point is defined, and like it's continuous, like there's no jumps or discontinuities on the curve, then you can see that the limit of f of x as x approaches c is the same thing of f of c. So as you get really close to here, you approach f of c, you also approach f of c from the right as well. So for example, the limit of sine of x as x approaches c is the same thing as sine c, because sine of x is continuous for all of its domain. Okay, so let's talk about some trigonometric limit properties. So the limit of sine of x divided by x as x approaches 0 is equal to 1. And the limit of 1 minus cosine x divided by x as x approaches 0 is equal to 0. And you can see this visually here. So this is the graph of sine of x divided by x. So let's say this y equals, yeah. So you can see here as x approaches 0 from both sides, you reach a single number 1. And for the cosine property, you can see that as x approaches 0, the function also approaches 0. Although the limit exists, f of x is not defined there. Oops, should have put f of 0. F of 0 does not exist. Okay, so these limits exist because of the squeeze theorem, which is something that we're going to be talking about in a little bit in L'Hopital's rule. However, L'Hopital's rule will be explained later on because it requires some knowledge of derivatives. So let's talk about one-sided limits. These are limits that approach a value from only one side of the graph instead of both. And they are written as the limit of f of x as x approaches c from the left. So this negative symbol just means from the left. So you're going from the left, so you go to here, and let's say this is like c over here. This is c. And the limit of f of x as x approaches c from the right is like you start from here and you go to the right from here. So essentially you just have some point c, like say this is c, and c negative is from the left and c positive is from the right. So basically what I just said right now, c negative means that it's approaching c from the left, and c plus means that it's approaching c from the right. So let's say we have the limit as the absolute value divided by x as x approaches 0 from the left is equal to -1. So you can see here that we're currently -1 for all the way over here, and when we reach 0, we reach -1. And the limit of the absolute value of x divided by x as x approaches 0 from the right is equal to 1. So you can see here it reaches +1. However, the limit here does not exist. So you say like the limit as x approaches 0 of f of x, where we say that f of x is this. Oh, right here. Where we say that f of x is this, right? That does not exist because the limits from the left and right sides do not equal. So they do not approach the same value. So these are some reasons that a limit might not exist. So the limit value of f of x or y from the left is not the same as from the right, which is what we just showed over here. Because this one is -1, but over here it's +1. These do not equal. The second reason is that the limit approaches positive infinity or negative infinity. So like you have some function like this, and let's say the c is equal to 0. So if you go from the left, like the function goes up here, but since it goes to infinity, infinity is not like a defined finite number. So a limit must be a single number that is defined. If the number is not defined, then that means the limit does not exist. And the third reason is that the function oscillates between two y values as x becomes very close to c. So the first one, the limit of f of x as you approach c from the left does not equal limit of f of x as x approaches c from the right. So this is the first reason. The second reason shown is that the limit of 1 over x squared as x approaches 0 equals infinity. The limit can equal infinity, but that's just like another way of saying that the limit does not exist because it reaches such a big number. So these are basically the same thing, but this one just tells you more information. It tells you why it doesn't exist. It tells you that it reaches a very big number. And the function over here is the one that I already drew over here. And for the third reason, imagine you have the limit sine 1 over x as x approaches 0, but if you were to do that, the function would like oscillate a lot between -1 and +1. So that would just not exist. So let's show the first one and the second one. So the limit value f of x from left is not the same thing. So let's say we have the function y equals 1 over x. So as you can see, the limit as you approach, let's say limit as x approaches 0 of f of x, right? As you approach it from the left, you go to negative infinity, but if you approach it from the right, you go to positive infinity. Since they're not the same thing, they diverge from each other, that means that the limit does not exist. So like the limit from the left does not equal the limit from the right. And since they reach infinity, the limit also doesn't exist again because they reach infinity, which is a number that is so big that it has no bound and it cannot be defined. So for this function, the limit doesn't exist for two reasons. The limit values are not the same and they both reach infinity. Well, positive and negative infinity. For the third one, where it says it oscillates from between two y values as x gets very close to c, this function oscillates between -1 down here and +1. So as you can see, it goes from here, then it just goes crazy in the middle. Which means, and there's like no easy way to determine what value it reaches. Okay, so this is the squeeze theorem. Basically, it says if h of x is less than f of x, but f of x is less than g of x for all x that is close to c, and if the limit of h of x as x approaches c is equal to L, and it's equal to the limit of g of x as x approaches c, then the limit of f of x as x approaches c is equal to L. Okay, imagine this is h of x right here. F of x goes through here, and then g of x goes through here too. So if h of x and g of x equal, and that f of x is squeezed between them, that means f of x has to be equal to the point where they both meet. And this is going to be shown in the next slide. So imagine we have the limit of x times sine 1 over x as x approaches 0. So you can see here, it's a really weird graph. It like oscillates a lot in the middle. But we can see that it gets very close to some number down here. So we can say that g of x is the absolute value of x, which is bigger than f of x. And we can say that h of x is negative absolute value of x, which is less than f of x as well. So when x equals 0, g of 0 is equal to 0, and h of 0 is equal to 0. But since f of x, this is f of x, but since that's squeezed in between g of x and h of x, that means that the limit of x sine 1 over x as x approaches 0 is also 0 due to the squeeze theorem. So these are a summary for techniques of evaluating limits. So you can use direct substitution, like you just plug in the value. So like you just plug in c into here and see what happens. This only works if f of c is defined on the function. The second one, you can use a table. So you can say like x over here, f of x at the bottom, and then you have like let's say we're trying to get close to 5. So you have 4, 6, 7, 3, 2, 1. So as we get closer to 5, let's say f of x is like 5, 10, 15, 16, 17, 16, 15, 13, whatever. So as we can see, like it gets closer to 17. This third one, we can graph the function to see what value like it approaches. We can use algebra to simplify some function. We can factor the limit. We can also rationalize the limit using a conjugate. We can also use the trigonometric properties talked about earlier, and we can also use the squeeze theorem that was also talked about earlier. Before we move on to the practice questions, we're going to have to analyze some graphs. So this says the limit might exist while the function at c might not exist, and vice versa. So like the limit might exist but the function doesn't exist there, or that the function exists there but the limit doesn't exist there. So let's begin. This first question asks us, does the limit exist at x equals -4? So like, does the limit approach the same value from both sides as it gets really close to -4? So this is the point we're looking for right here. So from the left, f of x gets really close to 4, so it approaches 4. And from the right, f of x also approaches 4. So yes, the limit does exist, and the limit of f of x as x approaches -4 is equal to 4. This second question asks us, does the limit exist at x equals 0? So we're going to be seeing what value does the function approach when it gets very, very close to 0. So from the left, it goes very, very, very close to 1. Although it doesn't reach 1 because there's an open hole. If there's an open hole in the function, that means that the function is not defined right there. So from the left, so limit as x approaches 0 from the left of f of x equals 1. But let's see if that equals the same thing from the right. So from the right, the function gets very, very close to 3. It actually reaches 3. But these two values are not the same thing. So the limit as x approaches 0 from the right of f of x is equal to 3. However, these two things are not the same, which means that the limit doesn't exist because the limit from the left must equal the limit from the right, which means that this does not exist. This third question asks, does the limit exist at x equals 2? So let's see. From the left, the function approaches positive infinity, but from the right, the function approaches negative infinity. But since these two values are not the same, the limit doesn't exist. And also, since the function approaches infinity, the limit doesn't exist because of that as well. So no, it does not exist because the limits from both sides are not the same thing, and they both reach positive and negative infinities. So this fourth question asks us, does the limit exist at x equals 3? So let's see. From the left, so 3 is right here, and we're trying to approach it. So from the left, we get closer and closer, and we reach the point 3, 1. Let's see if they reach the same point from the right. So from the right, it gets closer and closer to 3, and it does reach 3, and it's equal to 1. So the limit of f of x as x approaches 3 is equal to 1. So yes, the limit does exist, and it is equal to 1. Okay, so this fifth question asks us, what is f of -4? So we're looking at -4, this is x, f of -4. However, there's a hole right here, but there's like no point anywhere at -4, which means f of -4 does not exist because there's a hole right there. Okay, the sixth question asks us, what is f of 0? So at x equals 0, what is f of x? So by looking at the graph, you can see that f of x is defined at 0 at 3. So you can say that f of 0 is equal to 3. It can't be 1 because there's a hole in the graph, which means that f of x is not defined there. Okay, so this seventh question asks us, what is f of 2? So we see 2 is right here. We're trying to find what value f of 2 is. So we can see that these two intersect, which means that f of 2 is equal to 2 because there's a defined point right here. Okay, this last question asks us, what is f of 3? So by looking at the graph, we're at 3 right here, and we can see that, f of 3 is equal to 1. And we're done for this question. Okay guys, this is the end of part 1. The second part will cover some of the practice questions. Thank you for watching, and stay tuned for the next one.